So I have known Umesh for more than 30 years. I still have vivid memories of him and his brother, Vijay, going to theoretical computer science conferences, Fox and Stock, and the two of them just sitting down on the floor in the hotel lobby and treating everyone to a sarod and sitar concert. That was a long time ago, but I'll never forget this. Anyways, I was very, very pleased when some years later Umesh jumped into quantum information, and now he's become one of the most prominent, and has been for a long time now, computer scientists in the field. In particular, he was the first person to prove that it's possible for a quantum computer to achieve in polynomial time something that's not possible with an oracle. With a classical computer, even probabilistic, and even if you tolerate errors, that was the big thing. Until then, we didn't know that quantum computers could do anything at all that would be useful. But without further ado, let me give him the stage. So, thanks, Umesh, for being with us.
Thank you. Thanks, Sheil, for the introduction. And yeah, sorry about the delay. We've had various, various issues setting up. So thanks for your patience. And sorry for yet another delay here, but hopefully it'll all work out. I guess I understand, since we are not in presentation mode, this might keep switching off. So I'll try to minimize that. So let me say at the outset that this may not be a traditional tutorial in the sense that well, I'll try my best, but you may not end up coming away understanding the basics of this new subject. But what prompted me to pick this topic is that there's this very exciting new sort of sub area that's developing, which I wanted to tell you about. And so in the course of this hour, I'll just be able to give you an overview and give you a flavor of the kind of questions that this area talks about, and then hopefully it'll pique your interest enough that you'll actually go and look at it. Well, that's our image of quantum mechanics from a long time ago. That's Schrodinger's cat, and but I'm sure you know that quantum computation has changed that picture radically. So cat seems like a pretty benign kind of creature. But what quantum computing taught us is that quantum systems are really wild, right? So whereas classical systems of n particles, you need order n parameters to describe the state of the system. For a quantum system of n particles, you need exponential in n many parameters. And so depending upon what your goal is, this is either, it's either a boon or a curse. So if it's certainly a boon if you're thinking about computers, because you have this enormous computing power to tap into if you only find a way to do it. But then if you're doing other kinds of things that we like to do, if you're doing physics, then of course it's a curse, because it makes it really hard to analyze and understand quantum systems if they're this difficult to describe. And then there's also the issue of, well, if you are given a quantum system, how hard is it to control it and test it and understand it? So it's this side of the, so this second side, this curse is what I want to talk about today. So what is a complexity theoretic viewpoint, a computational viewpoint, tell us about this side of the equation? Okay, so if you want to think about it in the same terms as Schrodinger's cat, then maybe once we have the quantum computing view of quantum mechanics, we should really be thinking of quantum systems as being not a cat but a tiger, right? And so the question is, can we as classical beings actually tame this really wild beast, right? So that's really this emerging area about what can we computationally say about these systems? Okay, and can we put a leash on them? So again, just going back to the basics again, remember that the state of an n particle system, let's say it was n spins, you can represent it, it's a unit vector in a 2 to the n dimensional complex vector space. So the state is, the state is a 2 to the n dimensional complex vector. Okay, so now one thing we could ask is there a large class of such quantum states which you can actually reason about? That can't be the case. Sorry, I don't have reception here, so. I know. Okay. No, I'm sorry. It was an alarm that I had set. Change the time on the. Sorry about that. Okay. All right. Okay. So the question we can ask is, we know that a general state of a quantum system, an n particle quantum system, is much too complicated for us to deal with classically. But now, could it be that there are interesting large class of quantum states that we can actually write down on a classical computer, and then we can simulate in some way on a classical computer? So another way to think about it is we can ask, well, the Hilbert space is enormous, but could it be that there's a little corner of Hilbert space which contains interesting states for us? And you could even go further, and you could say, well, could it be that many naturally occurring states lie in this corner, so that perhaps if you want to tap into this exponential power of quantum systems, you have to go outside of, you have to really work at it, right? So this is one kind of question you could ask. The other kind of question you can ask has to do with the fact that we get limited access to the quantum state. So when we actually measure, we see one of these n-bit strings, x, with probability alpha x squared. And in fact, Holevo's theorem tells us we can obtain at most n bits of information by measuring the state of this n-qubit system. So now you could ask the question, well, given this limited access, and given that that the system itself is exponentially powerful, what can we do if we are confronted with a quantum system and we don't quite, if we want to test it, how well can we test it? Or if we want to control it, how well can we control it? So this is yet another form of this same question of how, classically, how much access do we have to these systems, in terms of understanding, testing, etc. And these kinds of questions, we'd expect them to become more and more prominent as time goes along, because you might have who knows, someday you might have a company that claims to have a quantum computer, and then you want to actually test that it's actually a quantum computer, and how would you do that, right? So here's a model in which you might want to test whether a quantum system is really behaving as expected. So if you want to take this a computer science model of saying, well, we don't really know what's inside this quantum system. We don't understand it. So let's treat it as a black box. But now the only way we can communicate with it is by performing experiments. But we are classical, so the way to think about it is we provide inputs which are classical, and if they are classical, we may as well let them be binary. So we think of this black box as having 2 buttons on it, labeled 0 and 1, and 2 light bulbs labeled 0 and 1. And so that's how we communicate with this black box. And now what we want to do is we want to understand what's the state of the quantum system that it starts in. Is it what it claims to be? And does it actually execute the desired dynamics? It's claiming to behave in a certain way. Does it actually behave in that way? So again, it seems like a question where we are at a very severe disadvantage because the quantum system is exponentially powerful. We are classically bounded. How could we possibly even? And then not only are we polynomially bounded, we are computationally, but also the bandwidth at which we can communicate with the system is extremely tiny, right? We can communicate with it in bits. The internal state is this exponential superposition. you might think we have no hope at all of making any headway, right? So these are the sorts of questions that we'll think about. So let me try to okay. So let me talk about these two questions in turn. So the first one of simulating interesting quantum states, and the second one of controlling quantum systems. So here's a set of here's a candidate set of quantum states that we'd be interested in, and these are very natural in physics, in condensed matter physics. So let's say that we have we have an array of particles, a lattice of particles, let's say in 2 or 3 dimensions, subject to some local Hamiltonian. So the interaction between the particles is described by a local Hamiltonian, where each term of the Hamiltonian describes, say, the interaction between nearest neighbors in this grid. Okay, and what we want to know is, given such a description, so the description of this Hamiltonian is very succinct, right? So all we need to do is describe each of these local terms of the Hamiltonian. And now what we'd like to understand is, can we describe the ground state of this local Hamiltonian efficiently? Right? This is sort of the an interesting coherent state. You just have to cool down the system enough to get to such a state. And let's say that the ground state is in fact even unique. So does it necessarily have a polynomial description? Now you might already notice that there's a trivial answer to this question, which is not very useful, which is obviously it does have a if the ground state is unique, it definitely has a succinct description classically. Because all you need to do is describe the Hamiltonian, which you can, because each term requires constant number of bits to describe, and there are only as many as, order of number of particles, many. And then you say, what I mean is the unique ground state of this Hamiltonian. So you specify the ground state of the Hamiltonian. So it's a perfectly precise answer, but it's also completely useless. So what do we really want? Well, what we want is a polynomial description that allows us to compute quantities that we are interested in. What are the quantities? Like energy or any local observable, right? So maybe 2-point correlations or any other observable that involves only a few particles at a time. And this is sort of the basic question in condensed matter physics. This is one of the basic questions in condensed matter physics. And there's this emerging field at the intersection of quantum complexity theory and condensed matter physics, which explores the computational complexity of these questions. Right? And it's been extremely fruitful to investigate these. The sort of a computational viewpoint has shed a lot of light on these questions. So let me try to explain why this connection has been so fruitful. So the reason it's been so fruitful is that there's a basic correspondence between two fundamental objects. In complexity theory, the fundamental object is constraint satisfaction problems, like satisfiability. So you're given a Boolean formula on n Boolean variables, and you want to know, is there a satisfying assignment to this formula? Or more generally, as a constraint satisfaction problem, you might want to know, is there an assignment that satisfies, what's the maximum number of clauses you can satisfy, or what's the minimum number of clauses that must remain unsatisfied no matter how you assign, pick an assignment for the Boolean variables. Now it turns out this is the direct analog of the local Hamiltonian problem, where you're given a local Hamiltonian that acts on n particles, right? And these terms of the Hamiltonian correspond to these local constraints or clauses in the constraint satisfaction problem. And then there's sort of a dictionary by which you can say, concepts here correspond to concepts there, right? So for example, the number of unsatisfied clauses corresponds to the energy of that state. So the way you think about it is that each term of this Hamiltonian assigns an energy penalty to a state, depending upon whether the state satisfies it or doesn't satisfy it, or partially satisfies it. And then a solution to this constraint satisfaction problem corresponds to the ground state of this physical system. And of course, the goal in these two cases is quite different. Out here, what you're interested in is combinatorial optimization, right? You want to find a solution that optimizes, for some computational reason. And here, you're interested in understanding the properties of the ground state because they determine properties of materials. Okay, so now, as I said, it's not just that we want a description, we want a description of the ground state, but we want to be able to compute interesting quantities related to the ground state, local observables, like the energy of the system. So the local Hamiltonian problem says, approximate the energy of the ground state given the Hamiltonian. So the input is a Hamiltonian, and you want to output a number, which is a close approximation to the energy of the ground state. And there's this beautiful theorem by Alexei Kitaev where he showed that this problem is QMA hard. Where this QMA hardness is the quantum analog of NP hardness. So the story about this QMA hardness is that Avi and Dorit had invited Alexei to visit the Hebrew University, and and Alexei was thinking on his way there that he had not proved anything recently, within the next month or two, or he had nothing very new to talk about, and he was thinking, what can I tell them that would interest them? And so on the way, he decided he would prove this result because it would probably be interesting to his audience. So maybe this is a there's a lesson to be learned from this, which is if you want an interesting new result in quantum complexity or something, you could try proving it, or there's another strategy, which is you pick a key person and invite them to give a talk. Okay, so now what does this QMA hardness of this problem tell us? Well, the QMA hardness actually tells us that we cannot really hope for what we wanted from general ground states of local Hamiltonian, because like NP hardness, we don't really know P is different from NP, so we don't really know QMA is different from quantum polynomial time, but we believe it is, and in fact we even believe that there are no sub-exponential size classical witnesses for QMA complete problems. What that means is that we don't expect any kind of polynomial description of a ground state of a local Hamiltonian, which will allow you to check that the energy is what it's claimed to be. Right? So you cannot even check, not leave alone compute it from that polynomial description. So what this tells us is that this is really a hopeless task. So now you could say, well, how about simpler systems? Maybe the most general QMA completeness problems, they involve an interaction graph, and it could be very complicated. And so over the years, there have been a sequence of results that have made these, that have proved hardness, QMA hardness, and otherwise for simpler and simpler systems. So there was a result showing that it's even QMA hard for one-dimensional systems, which actually was a very big, which was very interesting to people in condensed matter physics, because 1D systems, they regarded as being easy. And in fact, you can see from a computer science point of view as well, because for a constraint satisfaction problem on one dimension, you have an efficient polynomial time algorithm. So this was quite a interesting thing. And then to add insult to injury, there was this result by Gottesman and Irani, where they showed that in fact it's hard even for translation invariant 1D systems, which means that all of these the terms of the local Hamiltonian are identical, right? So you have the same term of the local Hamiltonian, which just keeps shifting. And so now, it's hard to think of an easier problem to try to work on. So the lesson from quantum complexity theory seems to be that finding ground and low energy states is hard even for 1D systems, so we cannot expect to simulate these classically. But then, on the other hand, condensed matter physicists have a long tradition of actually simulating 1D systems. So about 20 years ago, there was this heuristic invented by Steve White called DMRG, and it's been extremely successful in practice for 1D systems. So you can ask, well, okay, it works in practice, but surely there's some principled reason for it. It's like the simplex algorithm. So, it worked in practice, but there was always this belief that, well, if it works in practice, surely something's got to work in theory, in its neighborhood to make, it can't be that it works in practice just for no reason at all. And so that's what that's the question we can ask. Is there a principal phenomenon? So is there some clean, well-defined class of quantum many-body systems that we can actually analyze? And so the answer seems to be that there's this one more parameter that you should be looking at, which is the spectral gap of the Hamiltonian. So what's the spectral gap? So let E naught be the ground energy. So it's the minimum eigenvalue of the Hamiltonian. So remember, the Hamiltonian is going to be now a 2 to the n by 2 to the n Hermitian matrix. It's so the ground energy of the system is the minimum eigenvalue of that Hamiltonian, and let E1 be the second largest eigenvalue. So it's the energy of the first excited state, and so E1 minus E naught is the spectral gap. So now, if you look at the QMA complete Hamiltonians, then the spectral gap is 1 over polynomial in n. It turns out that there's this very natural subclass of Hamiltonians, which is the gapped local Hamiltonians. So the intuition is if you're not very, very close to a phase transition, you should typically have a gap. So these are systems where the spectral gap is a constant. So this corresponds to, in the classical case, if you have a constraint satisfaction problem, you say, well, there's a unique solution, there's a unique satisfying assignment, and now if there's not a satisfying assignment, if you look at the next, if you look at any other assignments which are not this satisfying assignment, they must violate at least one clause. And so the spectral gap there would be at least 1, right? So here we are saying the spectral gap is at least a constant. Now, why is this an interesting class to think about from the point of view of succinct description? Well, there was this beautiful theorem that was proved by Matt Hastings back in about 5 years ago or 6 years ago. This was a real breakthrough. He showed that ground states of 1D local Hamiltonians have a polynomial description as a matrix product state. It's a kind of tensor network. So what's important is that you can describe them, you can approximate them closely with a polynomial size description. So you can represent them on your classical computer. And so finding the ground state of a local of a 1D Hamiltonian, which is therefore in NP. Oops, sorry, what? Oh, yeah, okay. Okay, so now what about finding it in polynomial time? So the folklore was that this was an intractable problem. And in fact, there were some results by Schuch, Sirac, and Westrate which showed that there's a closely related problem that's NP hard. And it turned out that last year in a strengthening of Hastings' result, with Arad, Kitaev, and Landau, we actually showed that there's a sub-exponential time algorithm for actually finding the ground state, as finding this representation of the ground state. And so this seemed to indicate that the problem was not NP hard. And so then very recently with Landau and Vidic, we actually showed that there's a polynomial time algorithm to find such ground states. Now, so what this does is you could think of this as solving the mystery that I talked about, which is why is it that DMRG works so quickly? So in what sense are these problems easy? But then there's much more to do. You could see this as the first step towards doing, towards an area of a new kind of complexity theory, which asks, what are those quantum systems that you can actually simulate efficiently on a classical computer? And in fact, there's a lot of work on this, on trying to simulate two-dimensional and three-dimensional systems, quantum systems on a classical computer. And success in this would be really extremely significant. And so one way you can think of these results for 1D is that they provide a way to understand rigorously what are the ingredients that makes 1D easy, and perhaps we can start investigating whether something similar or some of these techniques can be adapted or extended, or new techniques can be added to deal with the 2D systems, right? So you could also imagine that maybe there's a conjecture to be made that in fact gapped local Hamiltonians, maybe together with some other added conditions, are always polynomial time simulatable, and perhaps that could be one way to make sense of the fact that even though quantum mechanics is so hard, that it's so powerful, that we can operate at a classical level and understand certain systems, right? Okay, so let me just take a few minutes to describe to you some of the ideas that go into these results, and then I'll talk about the second topic. Okay, so the main obstacle to succinct description of quantum states is entanglement. So if you have a quantum system and you divide it into two parts, then you know that you can perform what's called a Schmidt decomposition of the system, and you can write the state of the system as summation Ci ai tensor Bi, where the Ai's form an orthonormal basis for the A system and the Bi's for the B system. And now the Schmidt rank, which is a measure of the entanglement between the left and the right, is the number of non-zero terms in this decomposition. So for example, for the Bell state, the Schmidt rank is 2, because there are two non-zero terms here. And then there's a more subtle measure of entanglement, which is the von Neumann entropy, which is just the classical entropy of the Ci squared, which in this case would be 1 bit, right? And so now, entanglement is what makes it hard to represent efficiently, the state of a quantum system. And so there's this very general and beautiful conjecture in condensed matter physics, which says that if you have a gapped local Hamiltonian, let's say that's your system with nearest neighbor interactions, then what it says is if you take the ground state of the system and you divide the particles into two regions, so the inside and the outside, and you ask how much entanglement entropy is there between the inside and the outside in the ground state? Well, then the trivial bound would be it's proportional to the volume of the system, the number of particles inside, let's say. But what the area law says is that in fact the entropy scales as the surface area. It's the number of bonds, number of these interactions that you actually cut by the boundary. Okay. So morally what it says is that most of the entanglement sits at the boundary. And so, if that's the case, then you should be able to give a efficient description by just describing the entanglement at the boundary, and then once you describe that, you can sort of cut the system into two, and you can describe the inside and the outside separately. So the data structure for doing this is called a tensor network, and so so this is really this is really a key to showing the area law and its strengthenings are key to showing that you can actually efficiently represent classical quantum systems. Now, of course, when physicists call something a law, what this means is, so this was this has been the area law has been in the folklore for a long time, and then it was actually precisely formulated in quantum entropy terms in this paper by Vidal et al. About 10, 11 years ago. And it was not until 2007 that Matt Hastings gave a rigorous proof for 1D systems. So in 1D systems, what it says is, if you cut your 1D system at any point, well, now what's the surface area? It's a number of number of interactions that you cut, which is exactly 1. So the surface area is 1. And so what the area law says is that the entanglement entropy should be bounded by a constant. And this is what he did. He showed that the entanglement entropy is bounded by this constant. It's exponential in log d, log of the dimension of the particle, divided by the spectral gap. Okay. Now, over these last 5 years, well, for the first year or two after Hastings' proof, we struggled very hard to try to understand it, and this was really quite a tour de force. And then we realized that to really understand the proof, we had to use our own techniques and try to do this combinatorially. And so, in the process of doing that, we actually improved this bound eventually to polynomial in log d over epsilon. So log cube d over epsilon, right? And in the process of proving this bound, we actually realized that it implied something stronger. It implied that there's a sub-exponential time algorithm for finding the ground state, and that's what started this thing off. Now, I should say that one of the most beautiful open questions in this area is proving a 2D area law. So for 2D systems, showing that the entanglement entropy is bounded by the surface area. So, in fact, even proving anything sub-volume, so showing that the entanglement entropy is bounded by any quantity that grows slower than the volume of the subsystem, that's already open. Now here's the other interesting thing. So if you can even improve this log cubed, the 3 in this exponent by the smallest amount, if you could improve it to log to the 3 minus delta, you'd already get a sub-volume law. Okay, so here's another way of saying it. This result is optimal in the sense that it's the hardest you can work without getting anything non-trivial for 2 dimensions. Okay, and if you could improve this to log squared, you'd prove the bound for 2D. If you could improve it to log d, you'd prove it for every possible dimension. So, okay, so that's the state of the art. Now, let me quickly say what is the actual ingredient that goes into this. So the main ingredient that goes into proving this area law is what we call an AGSP, an approximate ground state projector. So remember, so we're working in a 2 to the n dimensional Hilbert space. We have the unique ground state, and then there's a perpendicular space. Okay. So now imagine that you start with some state which has some angle with the ground state. So an AGSP is an operator. It's which you can apply to this state, and it moves it closer to the ground state. So it doesn't quite project it. What it does is it leaves the ground state alone, but it shrinks the perpendicular space by some factor delta. Okay, now the reason we don't want the projector itself is because we also don't want to increase the entanglement rank across this boundary by very much. So the entanglement rank increases by a factor of at most d, but the perpendicular space gets shrunk by a factor of at least delta, right? And now there's a race between these two. So if you can design an operator that wins the race, then you have an area law. Okay, and so what does it mean to design something that wins the race? Well, it must be the case that the shrinkage beats the increase in Schmidt rank. So d times delta should be less than a half. Okay, and if you manage to do this, then you would have proved that the entanglement entropy across the boundary grows as order log d. Okay, so that's how you prove an area law. Now, it turns out this AGSP is not just a way of proving the area law, but it's actually a very interesting object. It's sort of it's sort of a local object that you know, so this gap condition, the fact that there's a spectral gap, that's a global condition of the system. This AGSP is a much more local object. And so it turns out the Shuk, Sirac, and Vistrate result that I mentioned, which showed that this closely related problem was NP-complete of finding a succinct description of the ground state for 1D systems. So here's what it was showing. What it said was, you know, they said, well, a gapped 1D Hamiltonian means that you have a polynomial size classical description as an MPS. And then they said, well, what else can you get out of a gap? Well, you know, it's hard to see what else to do with it. So let's formulate the question saying, suppose you have a polynomial size description of the ground state as an MPS. Can you find it without using the gap condition any further? And the answer is you can't, it's NP hard. So what did we do to actually design an algorithm that finds this ground state quickly? Well, what we did was we said the gap implies an AGSP, and now we actually use the AGSP in our algorithm for finding the ground state quickly. Okay, and that's why it suddenly becomes possible to do so. So I don't think I'll go into details about the algorithm. If somebody wants to, I can do that at the end of the talk, or maybe afterwards. So I'm just going to skip this part about the algorithm and move on to testing quantum systems. So maybe since I'm moving on to the second part of the talk, I'll see if anybody has a quick question. Yes.
Basic one on about page. Basic question on about page 23 when you had log cubed of delta over epsilon.
Oh, yeah, d over epsilon.
I got a little. Sorry, d over epsilon.
Yeah.
I got lost. What were the definition of d and epsilon?
Oh, right. So yes. So d is the dimension of each particle. So each particle is a d state system. So if there are qubits, then d is 2. Okay. And epsilon was the spectral gap. It's the gap between the ground and it's the difference between the ground energy and the energy of the first excited state. Oh, that's a very good point. Maybe it was a log of order d. You're right. Yes. Or we could say the log is to a different base. Thank you. Okay. All right. So, yeah. Okay. Okay. So let me move on to the second topic about testing quantum systems. So, so here's a scenario again that we want to investigate. So we are given a quantum system. We don't trust it. We don't trust what's going on inside. We want to test what's going on inside. So, so because because our interaction with the system is necessarily classical, we may as well think of it as binary input, binary output. And so now we are given. So imagine that we are given this box by an adversary. It's supposed to have a certain input output. You know, it's supposed to behave in a certain way. So it's supposed to be initialized to a certain quantum state, and it's supposed to evolve the quantum state in a certain way in time. And it's supposed to react in certain ways when we give it inputs. What we want to do is test that it's really doing what it claims. Okay? Now, it should be obvious that this is too tall an order, right? Because obviously, instead of, what could be going on inside this box is really the private world of this system. It could be, what it could be doing inside is it could be doing a classical simulation of a quantum system. So how do we know that what's going on inside is really what's claimed, that it's really that quantum state evolving in the way that it was supposed to be? So now, instead, what we're going to do is we're going to generalize this question just a little bit. So instead of having one quantum system, we'll assume that we have two quantum systems. Okay? But both are untrusted. So the adversary can do twice as much mischief as before. But now the thing that we are going to count on is that the two systems are allowed to be entangled. And again, what we want to do is we want to verify that the system started in the claimed initial quantum state and it executes the desired dynamics. And so the surprising thing is that once you pose the question this way, there is actually a solution. There's a way that classically we can actually force the system to behave in the way that it claims to have behaved. We can test the input-output behavior and then claim with some confidence that the system is behaving as it was supposed to. Okay? So, and this despite the fact that the system is exponentially powerful, we are polynomially bounded, we have very limited access. Okay, so here's the scenario is that, this is the classical experimentalist. This is us interacting with these two quantum systems, and we want to actually understand how they behave. And so, well, what are the problems in making this happen? So the first problem is that the Hilbert space of each device could be very large, right? So how can we even characterize what's going on in there? And secondly, how do we know that, if on input, when we press this button, the device is supposed to measure the first qubit, right? How do we know that what it outputs is even the result of measuring a qubit? Maybe it could be doing something completely, arbitrarily complicated on its arbitrarily complicated internal state. So how do we ever constrain this incredibly powerful object from, to do exactly what we want it to do? So the secret to this is these, those Bell type games, the Bell inequalities. So in particular, here we're going to use what's called the CHSH game, which, these are sorts of, a kind of test of quantumness that were discovered in the 60s by Bell and CHSH and so on. So this is a particularly nice game, which I'm sure many of you have seen, but, if you haven't, let me describe it to you. So you have two distant parties, Alice and Bob, can't communicate with each other, and but what we're going to do is they're playing a cooperative game. So they're trying to cooperate with each other against a referee who gives each of them an input, which is a random bit. So Alice gets as input a random bit X, Bob gets as input a random bit Y. And now they're trying to coordinate the output to give the same output bit, either both zeros or both ones, unless X and Y are both 1, in which case they want to give opposite outputs, either 0, 1 or 1, 0. So now, you can think about it a little bit, but classically it's impossible to succeed with probability more than 3/4. So really the best that Alice and Bob can do is always output 0, and they win in the 3 cases and lose in the 1, but they just can't do any better. But if Alice and Bob share they share entangled qubits, then they can achieve a success probability of cosine squared pi by 8, which is about 0.85. So this is a test that, if you run this experiment and you see that they succeeded with probability close to 0.85 or greater than 0.75, you've tested quantum mechanics, right? Or it's a test for quantumness. Now, how does this actually work, and what do they actually do? Well, well, Alice and Bob share a Bell state or EPR state. It's a state in the it's 2 qubits which are in the state 0, 0 plus 1, 1 with equal amplitudes. And now, what they do is, if Alice, if she gets a 0, she measures her qubit in the 0, 1 basis, and if she gets x equal to 1 as input, then she measures in a basis rotated by pi by 4. Bob, if he gets 0, measures in a pi by 8 basis, and if he gets 1, he measures in minus pi by 8. So what's the significance of these bases? Well, what you can see is that in 3 out of the 4 cases where they are supposed to output matching bits A and B, they measure in bases which make an angle of pi by 8 with each other. And it's a property of the Bell state that if Alice measures her qubit in a certain basis and Bob measures it in a different basis, then they get matching answers with probability cosine squared of the angle between the bases. So you get cosine squared pi by 8 in these 3 cases. In the 4th case, the bases are 3 pi by 8 apart. And so they get matching answers with probability cosine squared 3 pi by 8. But in this case, they are supposed to, in this case, what they are supposed to do is output opposite bits. So they get opposite bits with probability sine squared 3 pi by 8, which is the same as cosine squared pi by 8. And so in each of the 4 cases, they succeed with cosine squared pi by 8, and that's the beauty of this. So if you want to, another way to think about it is, this is a semi-definite relaxation of the problem. So classically, you get the integer solution, and quantumly, you get the semi-definite programming relaxation. Okay, now, so the first step in controlling, in this protocol for commanding a quantum system is to prove a rigidity theorem. So what does this rigidity theorem say? It says, suppose that Alice and Bob play this game and they win with probability close to 0.85. So they win with probability at least 0.85 minus epsilon. Then the only way they can do this is the way that I said. If they use the protocol that I said, or something that's square root of epsilon close to it in a suitable norm. Okay? And, of course, Alice said, Bob, we don't want to take away their privacy, so, of course, what they do in their devices is their own business, so all this is up to a unitary change of basis within their devices, but really the way they behave must look like what I said, up to a change of, up to how they want to arrange their internal memory. Now, what's even more interesting is, suppose we play a sequence of such games. Okay, so we play a bunch of such games. We input x1, x2, x3, x4, y1, y2, y3, y4, and have them output. And suppose they win close to 0.85 fraction of the games, then what we can actually conclude is that they must have started with a tensor product of many, many such Bell states, and then in each step they measured them according to that strategy. Of course, up to unitary changes of basis. Okay? So now, at this point, I don't know, how many of you have seen these martial arts demonstrations, if you've ever seen an Aikido demonstration where there's this little Japanese Aikido master who can, 80-year-old master, and then confronted with this huge hulking person, extremely fit, and then, he sort of goes into this thing, grabs hold of that person's hand with the appropriate handhold and the wrist locked in a certain place. And now this person, if he moves his hand in any way, it's so painful, he just can't do it, right? So, basically this completely neutralizes this big hulking person, and now the master can sort of move him around by moving his hand around, and this guy has to follow, and he's got to follow exactly what the master said. So I claim that's what we've done at this point. We have this big hulking quantum system, and we've put it in this hand lock because Because what we've done is every time we give it as an input, it has to behave in exactly this way. And now what we want to do is we want to, having gotten into the wrist lock, we want to move it through the paces, and this way of moving it through the paces is called quantum computing by teleportation. So we do, okay, so sorry, we do two things. We use tomography. So what we do is we can leverage the fact that we have this hold, and we can get them to do so first these simple operations, and then we build up to slightly more complex operations, and then we can use computation by teleportation to get completely arbitrary dynamics. So what that means is that, you know, this is a system by which this purely classical experimentalist using, you know, extremely limited means and simple tests can actually take this quantum system through any arbitrary dynamics of, you know, that are specified. Okay, so what are the things that follow from this? Well, one place where this sort of thing comes up is in this area of device-independent quantum key distribution. This is something that I'll talk about tomorrow, and in fact, you know, so maybe I'll save this for tomorrow. Okay, since I'm running short of time, I should say that you know, there's this whole other question about testing that a claimed quantum computer is really quantum. And in this area, there were two very beautiful papers which actually inspired this whole, you know, this whole sequence of results by Aharonov, Ben-Or, and Ivan, and Broadbent, Fitzsimmons, and Keshefi, where they said, well, suppose you have this classical verifier who's trying to test this quantum system, and ideally, you know, all you want to do is interact with the quantum computer classically, but, you know, since they couldn't actually make that work, they said, well, let's also assume that you have a small quantum channel. So the verifier has, you know, can manipulate, say, a constant number of qubits, and can exchange those constant number of qubits back and forth with this system. And then they showed that you could actually test any computation in quantum polynomial time in this kind of model. Now, you can actually take this a step further. You can say, well, what about if instead of testing a particular quantum system, you want to test quantum mechanics itself? Now, why would you want to do this? Well, here's why. So, you know, what physicists like to do is they like to test the limits of their theory in the limit of high energy or very small sizes or at very, very, very large velocities. And every time physics has been tested in one of these limits, something new has emerged, something very interesting has emerged. So, you know, because maybe the physics broke down the way it was thought to be, and something completely new emerged in its place, which, you know, where the old theory was a special case of the new one. So now we could say, well, this exponential growth, this exponential power of quantum systems, this is probably one of the most counterintuitive aspects of the theory. And so surely we should be testing quantum mechanics in this limit of high complexity, right? But then there's a basic problem that comes up, because, you know, what do you do when you test? Well, you theoretically predict the outcome of an experiment, and then you actually test against, you perform the experiment and see if it matches up to within experimental error. But now if your theory is exponentially hard to simulate, how are you going to do that? Right? So how do you even carry out this first step? So here's a way you can think about it. So you know, in complexity theory, we have this notion of interactive proofs, where you have a verifier who is weak, or, you know, more like an Arthur Merlin game, where Arthur is rather, you know, is not terribly smart, but then he has access to Merlin, who is a prover who is extremely wise and who can answer all kinds of questions, except Arthur doesn't trust Merlin. And so the question is, you know, what are, by carrying out these interactive proofs, where they interact for a while, if Arthur follows these proofs, he can convince himself about the validity of really quite remarkable claims that Merlin makes. So now we could think of performing an experiment, a quantum experiment, as being this kind of an interactive proof, right? So instead of first deciding the experiment and saying, I know what answer I'll accept, and then going and performing the experiment to see whether it matches up, you actually, do a much more civilized thing. You go into your lab and you carry out a conversation with your physical apparatus, and at the end of the day you say, okay, I'm satisfied, everything is fine, or you say, look, never, this is completely wrong, right? So that would be an interactive experiment. So now, can one actually carry this out? Well, if we substitute quantum mechanics in the place of Merlin, and we carry out this interactive proof, we are really asking whether anything in quantum polynomial time has such an interactive proof. And at first sight, the answer is obviously yes, because quantum polynomial time is contained in P space, which is IP, which is this class of problems that you can actually verify by such an interactive proof. But the problem is, in IP equal to P space, the power of the prover has to be equal to P space. Here, since we are working with quantum mechanics, the power of the prover has to be BQP. And so the question is, is our interactive proofs with BQP bounded provers as powerful as BQP? And that's a very beautiful open question. So for the moment, we know that with two provers we can do it, but with those two provers we still have to assume something about quantum mechanics. So we really want to solve this problem with, in this one prover setting. And I think this is it's a really beautiful open question. Okay, so this is the open question. Okay, let me say one last thing then, and actually, let me not say this one last thing. Let me just move on and say a different last thing. So I don't know how many of you know that there's this new Simons Institute for Theoretical Computer Science at Berkeley. It started its operation as of this week, and the goal of this institute is to bring a computational lens to bear on the sciences, to have this interaction between computation and the sciences. And so, every semester there are going to be 2 programs on 2 different topics, bringing in various, long-term visitors, postdocs, short-term visitors, workshops, and so on. And so, in the spring, we have a program on quantum Hamiltonian complexity. So, on the kinds of topics that I've been talking about here today, and there'll be 3 workshops dealing with quantum games and protocols, complexity meets condensed matter, things like area laws and quantum PCP theorems and so on, and then simulations of quantum systems, efficient classical simulations of quantum systems, and quantum simulations. And there'll be a lot of there'll be many prominent researchers in the field, very distinguished researchers at the institute. And so, if you'd like to participate, you should really let us know. The actual program for the workshops and the boot camp aren't yet decided. So certainly there's room for people to participate. Okay, thank you.
There's a little time for questions. Specifically, mine is 15 minutes. So the longer your questions, if they are in negative time, the better will be.
So essentially, when you talk about a rigidity theorem, I gather what you mean is if you have a CHSH kind of violation, like up to 85%, anything exceeding 75%, then you can certify, or if you're epsilon close to, I think, 85%, then you can certify that the choice of state and measurements was exactly the choice that's...
Games then, and you get, now you can actually see what fraction of games the two players won, and if it's very close to 85%, then you know that they must have been following protocol. Now what you do is you run many games, and then at some point during these games, you keep playing the game the way it was, the CHSH game with Alice, but with Bob, you change the inputs. You ask him to measure in other, in other bases. So you might ask him to measure two of the, instead of measuring only one qubit, you ask him to measure two of them in some bases. And you use Alice's answers to do tomography to check that Bob was really following protocol. And then you do the same thing at some other random time. You play this game where you have, you're playing according to protocol with Bob, CHSH, and then for Alice you ask completely different questions. So now what you can do in this process is you can check that when you switch, Alice is really doing the measurements the way you asked her to, and Bob is doing exactly what you asked him to do. And then at some point in the protocol you switch for both. And now what you can do is you can actually do this computation by teleportation going back and forth. So you ask Alice to prepare resource states, and you ask Bob to combine them, and in the process you're actually having them teleport back and forth and compute for you. And so this is how you do it.
Well, thank you, Umesh. Of course, this is a 1 hour talk to this entire topic. We should really move on, so if there is maybe one urgent question with a short answer, please feel free, and then we'll take a break.
I was pleased to see that on the program it called it a health break.
My idea. Charlie, good idea. We'll follow you. All right, then let's take the health break, and we'll reconvene at 10:45, and let's thank Umesh again. So at 10:45, 15 minutes behind schedule.